During a hands-on session, we will use the Datebreak Community Edition. The reason we choose Datebreaks is because then in that way we can control the version of different package, because Datebreaks has different runtime. By choosing a specific runtime, we can make sure everyone use the same version of different R and Python package, and then make sure you can repeat the notebook. But in case the cloud doesn't work, sometimes the server can be down. It happened last month when we taught this course. So in case that happened, you can also use the local notebook. We have a local notebook here. So for each hands-on, we have the Datebreaks notebook, we have a local notebook, and also Python notebook. So for the local notebook, you could run it locally, just need to set up the Python correctly. So you can have run into some problems. I ran into some problems and I did some search. So its solution for the problem I had, it seems pretty common. So if you had a similar problem, you can refer to this, try to troubleshoot. Because Keras package basically is an interface to the Python, Keras and TensorFlow. So you need to install Python as well in the backend. And then we will go back after 10 minutes. Yes, so you will go to your workspace and click user, and you will see your username. Get into your space, and then you go import, and then you pick URL, and then you go to this website. You copy paste the URL of the you do import, and you import. Yep. Since I already imported, so I'll cancel. And then you can click. It's better to click just run all, because one cell depends on the other. So you just run all cells in this notebook. You click run all cells in this notebook, it will start to run. Okay. As I said, Keras will actually use the Python, the R Keras package use the Python Keras package, which use the TensorFlow as the backend. So you need to first install R Keras package. It takes some time to install. And then you do library. You also need to install Keras. This function will install the backend Python package. So this data set, the handwritten digit data set, is already in the package. So you can just use data set minst to load the data. You can see it loads the data. So you're already familiar with the data, because when we go through the Feedforward neural network, we already introduced the data. It's a handwritten digit. The training set has 60,000 image. It's a 28 by 28 pixel grayscale image. So each pixel would be a number between 0 to 255. So it's a 28 by 28 matrix. A testing set would be 10,000 image, and you have the response variable. That's the label of the digit, handwritten digit. So you can see the structure of the data would be input, the training data, X would be 1 to 60,000, and each input will be 28 by 28 matrix, and Y is 1 to 6,000. This is before you pre-process it. You need to pre-process it. Y. Right now, it's just the digit, the real digit number outcome. You can see 504. It's not a dummy variable yet. and testing is the same thing. So first you will need to read, you will need to get the training data and save it as an object. And then testing data, you save it as an object. And you can see it's the same. Basically, you save it as different object. So you can see so you can save all the object to separate it out to be X train, Y train, X test, Y test. And then you can see the image. This cell basically just you assign any of the image, and then you get the input matrix, and you apply. So you have to rotate it. It's because the way it is saved is rotated. You always need to rotate the matrix to see it as the right position, direction. And you can change the number to see another image. Uh-oh. Incorrect number of dimension. It's very strange. No, I don't know what's going on here. You should be able to change the number and plot it again. Now, if you need to go all the way. Yeah, you can change because I already pre-processed you can plot different number. And then when you visualize the input matrix, it's each one is a 0 to 255 pixel value. And then you need to pre-process the data. The first is you have to vectorize the image to be an array, because it's not convolutional neural network. We're not using convolutional neural network, so it doesn't handle the matrix. So you need to vectorize it. So this basically vectorize the result, and then vectorize the input, and then you need to rescale to be between 0 to 1. It actually make a big difference. You rescale it or you don't rescale it, the model accuracy will be different, because rescale it will help the propagation process, the optimization process. So you need to rescale it. And then after this, you can see the new data shape change to be 1 to 60,000, and you have 784 features. And then you need to pre-process the outcome variable. You have to make the outcome variable to be a categorical, the dummy variable, 10 different dummy variable. The current outcome variable is, if you remember, the current outcome variable is just a digit number, like 60,000 and digit number from 0 to 9. And then you need to make it dummy variable. So you have 10 columns. Right, you have 60,000 image and you have 10 columns. Each column will indicate that image, if that image is specific digit. So then you encode this to be dummy variable. Then you can start to fit model. So in Keras, it's very easy to fit the model if you know what layer you want and how many unit you want. Like if you know an existing model, you want to, not too complicated, you want to replicate this model, and then you can just basically stack up those layers. In this model, you'll have, first you need to initiate a sequential model object. So it's a DNN model. And then you start to stack up all the layers. The first layer is dense layer. So you say you have 259 units. That's the neurons you want. And activation function use value and input shape. First layer, you need to specify input shape. That's 784. Yep, that's 784. And then you have a dropout rate is 0.4. So it will randomly drop out the percentage of 0.4% of the neuron. in each iteration. And then you stack another layer that is another dense layer, it's 128, and use activation function value, right? And then you set another dropout, and then unit, and you add another dense layer that's 46 neuron, and then use value and drop out again. You note the last layer, that's an important one. The last layer, you use unit 10. You can't, so for the previous layer, you can change, you can try to increase the number of units, see how it works, or decrease the number of units. You can do your own magic to change this. But for the last layer, you need to use 10 units because that's the shape. You have to match the shape of Y. Y here has 10 columns. That's your category, number of category. So you need to use 10 units. And then the activation function is softmax for this one. So then after you run this, you basically already initialize this model, and this model has 4 layers. First layer has 255 nodes, second layer 128, and third layer 64, last layer 10. Dropout doesn't count as legitimate layer. It's basically a regulation, try to prevent overfitting, but it's not a layer. And the activation function for the first 3 layers are all value, and the last layer is softmax because you need to connect it to the final result, the outcome. And you can get the model detail using summary, use model summary. Up until now, you haven't started fitting the model yet. You basically define the model. Up until now, we haven't fit any model yet. We just basically define the model. You can see the number of parameter in this. This is a very small, very small example. We have total parameter 242,000, about 243,000 here. And if you remember the number of image, we only have 60,000. So you can easily pass number of parameter will pass the number of sample. Now you start to compile the model. So you already, so far the DNN model, you already defined the DNN model here. So you're already defined some of the model structure, and you need to further define what's the loss function you want to use. Categorical entropy is a very common one. An optimizer here, we use RMS prop. If you remember, RMS prop will adjust the direction and also adjust the learning rate, the magnitude you want to learn. So it's a combination of the two. You can also change different optimizer to see how that's going to impact the conversion. And here you compile the model. So the DNN model include all the structure, and you do compile, and you add in more information like loss function, what optimizer you want to use, and the metrics. You use accuracy here. You want to it will show you the accuracy. And then once you have defined all of this, you can start to fit the model. And when you fit the model, you need to specify more things. You can see there are so many different hyperparameter that you need to decide. And then you need to define how many epochs. You can have 20 or 50 epochs, things it takes time to run. I put 15 here. And then the batch size, I use 128. That's a typical batch size, mini batch size, more specific. And validation split is 0.2. This is the validation split in training data. It's not using the testing. Testing data is just for testing. This is just used to train model. They use validation split because you need to apply on the validation data to know the accuracy. So then after this, you will start to fit the model, and it will start it just shows you the process of fitting the model. So you can see how it changed after each epoch. It will show you how it changed after each epoch, the loss function. And this doesn't take too long to run, less than 1 minute. Actually, installing the package take longer than running this, and also it's a very simple model, so it doesn't take too much to run. It will take longer when you do RN and the CN and RN. And then you can see the structure of the DN history. And you can plot the DN history so you can see the loss and the validation loss. The loss is the loss in the training data. Validation loss in the validation data. That's the 20% you left out. So this is the accuracy. So you can see about around 11 epoch, around there. If you look at the loss, it's about 10 or 11, maybe around 10. You will start to see the loss increase again in the validation set. So you might just choose 10 or 11 epoch instead of using 15. If you add more epoch, you could see a further trend. And validation, the accuracy, you probably can see that accuracy on validation can be higher than accuracy in the used to train the model. It's not necessarily in general you will see the trend, but in specific sample you could see validation accuracy higher. And then you can use that to predict the test data. You didn't so far. We didn't use the text data to build the model, and then you can use the DN model object. So when you run this, even you can see that can be something confusing. You don't see anything assigned to this. You don't see anything assigned to this DN model, but once you run each of this cell, it actually gets attached to the object DN model. So the DN model has more information than the beginning at the beginning. So here you can use the model you have to evaluate the test data. So you can see the accuracy is 0.97, about 0.8, 0.98 on this testing data. And you can also check the prediction, top of the prediction.